Okay, so now for the last part of today's lecture, let's start with some variants of the convolution operation. So in particular, we will have a look at these types of convolutions. Okay, so 2D convolution is the one that we have seen so far in this lecture. So you guys hopefully are super familiar with this now. And just one thing to note here, that the weight matrix corresponding to this 2D convolution, if we have NN input channels and output channels and K1, K2 kernel size, the weight matrix is this guy. Okay. Now, 3D convolution is basically extending 2D convolution to 3D, which means that I can now have my input images can be 3D volumes, which is very relevant in medical imaging, where it's common to acquire images as 3D volumes. Okay, so if I have a 3D volume as my image, my kernel size itself has to be in 3D. Okay, my kernel has to have K1 times K2 times K3. Moreover, on top of that, there will be a certain number of input channels. So for example, if I have two modalities, MRT1 and MRT2, both acquired in 3D, it may be possible to take both of those 3D volumes as input and do some analysis on that. So in that case, we can have NN to be 2. But in general, NN can be some number. And then the total kernel size would be NN times K1 times K2 times K3. Okay. And then we would slide that kernel through the volume. So we will slide it through this volume and then move it along the other axis and then slide it there and so on. And then we will get an output like this. And this would amount to getting one output channel from the 3D convolution. And like this, we can have several output channels. Okay, so 3D convolutions are very nice for basically integrating 3D information. So allowing this convolutional filter to capture not just 2D spatial correlations, but also 3D spatial correlations. However, they come usually with a huge memory cost. And this is an area of active research, especially in medical image analysis, as to how can we get 3D convolutional networks to work well in a more memory efficient way. Okay. Okay, then there is this idea of one-by-one convolutions, which basically means that I have a convolution where the kernel size is 1 by 1. Okay, which means if I have a certain number of input channels, and then this will be my convolutional kernel, and I will place it on top of the inputs here, and I will have a 1 by 1 kernel size, which means I won't be integrating any spatial information in any of the channels. I will simply be combining the information in different channels pixel wise. Okay, and this is useful in some cases where you don't want to mix spatial information, yet you want to combine the information in the feature maps. Okay, so that is one by one convolution. Then there's this idea of dilated convolutions. The motivation for this is, so here I have a 3 by 3 convolution, which let's say the receptive field that I get from this, which is 3 by 3, let's say this is not sufficient for my application. So one way to increase the receptive field is to have a 5 by 5 convolution, for example. But now here I had 9 learnable parameters, but here I end up having 25 learnable parameters. So you recall that having more number of learnable parameters is somehow not a very good thing, right? Because we increase the risk of overfitting every time we increase the number of parameters of our network. Let's take that as a general rule of thumb. So dilated convolutions try to avoid this problem by having a 5 by 5 kernel where there are only 9 learnable parameters and all the other parameters are zeros. Okay, so in fact they take a 3 by 3 kernel and then basically insert zeros in between those in between that matrix. Okay, and if they insert zeros like this, then it's called a dilation rate of 2. But then you can have higher dilation rates where, for example, you can have 2 columns of zeros between every 2 non-zero kernel values or something like this. And this allows you to get a higher receptive field without an extra cost in the number of parameters that you've introduced. Okay, so that was dilated convolution. And then finally, we want to look at transposed convolution, which basically serves the purpose of increasing the spatial extent of the output as compared to the input. So recall that in normal convolution, we always had this property that the output size would either be the same or would be smaller than the input size. But for some applications, for instance, for image segmentation, for example, after we have reduced the um, representation size, at some point we would also like to increase the representation size back to the original resolution because our output is of the same size as the input. And therefore we need some mechanism to have this increase in resolution. And transposed convolutions provide that, and they provide it like this. So let's say you have a 2 by 2 input and you want to increase the size of this guy. So what you do is basically you pad zeros around it. Okay, so you pad zeros like this, and then you simply do normal convolution on this padded guy. So you introduce a 3 by 3 convolutional kernel here, and now you apply a normal convolution. So you just place it on the top left corner, get the dot product, and you get your number, and this is the output number here. And then you can slide the convolutional kernel just like in normal convolution, and you end up getting output which is bigger in size than the input. And actually, if you have a certain output size that you have in mind, then you can pad zeros accordingly here, and then you can end up getting that output size. Right? So this is transposed convolution. Sometimes in the literature, this is referred to as deconvolution. This is actually incorrect usage of the term because a deconvolution actually refers to the exact inverse of convolution. Okay, transposed convolution does not provide that. Transposed convolution only provides a resolution upscaling, but it is not actually inverting um, uh, the convolution operation. Okay, so the use of deconvolution also, although quite prevalent in the literature, it's a bit of a misnomer. You should try to avoid it. Transposed convolution is the right term for this operation. Okay, so now we have looked at these few variants of the convolution operator. Now finally, let's look at a simple image segmentation CNN. Okay, so for image segmentation, basically there are two competing factors. Okay, so again, image segmentation is the problem of going from the image to another image where for each pixel we have a certain class assigned to it, right? And now just let's think about what it takes to assign a certain class to a certain pixel. First of all, we need to we need to see these boundaries here, right? So we need to distinguish between neighboring pixels according to the boundary. So we need to pay attention to this local information. On the other hand, if we just concentrate on the local information, we won't be able to accurately classify the correct organ in this case. Okay, for that we also need the larger context of where that organ is situated. For example, if I am just zooming in on the small region here, I will not be able to say whether that region belongs to a certain organ or not. For that, I need to look at this larger region, and then I can make my decision. So there are these two kind of opposing factors, one which wants you to look at a larger context, and the other which wants you to really concentrate on neighboring pixels and make a decision based on that. Because the context is going to be the same for two neighboring pixels. But still, if there's an edge in between them, then those two pixels should get different labels, right? So let's see how we can design a CNN which is able to take care of both these considerations. Okay, so this is the CNN that is our friend by now, hopefully. So this is the classification CNN, and let's see if we can start with this, and then sort of work towards making it be a segmentation CNN. Okay, so here we have convolution, max pooling, vectorizing, and fully connected layer, right? So obviously now we don't want a fully connected layer because we're interested in getting an output which is of the same size as the input, right? So let's start by just getting rid of that first. So now we just have convolutions and max poolings, okay? Now I will just rearrange this. So this is just, taking it like this, taking the thing that I had before and just making the lower resolutions actually go down a little bit. Okay, and you will see why I do this. Why I do this is because I want to add this other layer here. So what I did, I had this before, and I added a convolutional layer here, followed by an upsampling layer here. So you recall how we discussed transposed convolutions, which allow us to upsample the output as compared to the input. So we can have, for example, a transposed convolution here. Or we could also simply have a bilinear upsampling of the input here. Some kind of upsampling here, followed by a convolution, then another upsampling, followed by another convolution. So you see these upsamplings allow us to regain resolution and then come back to the resolution of the actual image. Okay, so now we have what is called an encoding path. So basically we are encoding the content of the image into some low dimensional representation. And then we have a decoding path, which is taking this low dimensional representation and decoding back the segmentation of the image. Okay, and because of these max pooling steps, we end up getting a fairly large receptive field, right? Because every pixel in this guy here is looking at a fairly big area in the input image. So, as we said before, we have two considerations for the segmentation problem. We want to focus on um, uh, local regions to see edges, but we also want to focus on larger context. So by having an architecture like this, we have solved one of those problems. Due to these max pooling operations, we have a large receptive field, and therefore we can look at large context while making a decision about our segmentation. And how we take care of the other problem, which is to look at local regions, is by adding these what are called as skip connections. Okay, this was introduced in this paper here, which is one of the most cited papers in medical image analysis in the last few years. And it's a very neat idea actually. So what they propose to do is simply add a connection here which takes these feature maps and concatenates them to these feature maps. Okay, and then this convolution has number of input feature maps, not just this, but actually this and these. All these are, so these and these, all of them are inputs to this convolutional layer. Okay, so and then similarly at this level again, you have these guys which are concatenated to these guys. So you have and they act as number of input channels to this convolutional layer. So you have local information in this which has not been lost due to the max pooling operations, this local information is directly transferred to the output, and it can be used for making local predictions here. Whereas these max pooling layers give you large context information, which can be used via these upsampling steps, again to make predictions about the segmentation. So this is how both the considerations are taken into account. And that's it. So we have this, uh, the simple segmentation CNN, because we could really build it up from the very few building blocks that we have learned. And then it turns out that it can really do a remarkable job on a wide variety of image segmentation problems. Okay, so with that, we come to basically the end of today's lecture. And yeah, I hope it was helpful for you guys. If you have any questions, please feel free to write to me. I will. Actually, I forgot to put my email on this, but I don't know how you guys, ask for clarifications or something. I will talk with Ender about this, and I will let you guys know. But yeah, I hope you found it useful. And towards the end, I would just like to say, for further reading, if you guys are interested, this book, Deep Learning, I find it to be extremely nice. It's really available online. It's, I think, very well written. It's not too mathematically dense. The writing is quite easy to follow. And especially these two chapters on neural networks and CNNs are something I can recommend you to look at if you guys are more interested. It may not be required for the purposes of the exam, but if there is interest from your side, you're more than welcome to have a read there. All right then. Thank you very much.